Jnanam Paramam Dhyayam. Knowledge is supreme.
Welcome to the 14th lecture of this course entitled Advanced Transition Metal Organometallic Chemistry. We have been looking at various kinds of transition metal complexes, their synthetic protocols, their structure and bonding, as well as their reactivity, particularly from the perspective of their utility in various kinds of catalytic reactions. From that standpoint, we have been discussing important type of organometallic compounds, and these are transition metal cyclopentadienyl complexes, particularly various kind of metallocene compounds. These compounds are not only unique in terms of their bonding features, but also they show unique reactivity when it comes to their property studies. And of the various metallocenes, we have focused on ferrocene, usual suspect of metallocene chemistry, in great detail to look at its bonding, structure, reactivity and property is. Now, in that perspective, we have looked into various reactivities of ferrocene in the previous class. Particularly in the previous lecture, we have looked at various reactivities. The one that stands out is the extremely facile reactivity of ferrocene towards electrophiles. Now, the reason for this extremely facile reactivity of ferrocene towards electrophile arises because of the carbanionic nature of the cyclopentadienyl ligands, which when bound to iron in ferrocene are still partially negatively charged, and hence they react extremely fast with electrophiles. Now, it seems very simple, conventional as well as expected, and this reaction is so fast in ferrocenyl complexes that they are about 3 into 10 to the power 6 times faster than that of benzene. Such kind of electrophilic substitution reactions. Ferrocene amines correspondingly are more basic than anilines, and ferrocenyl formic acid also is a weaker acid than benzoic acid. One of the conditions though for this electrophilic substitution reaction to occur is that the electrophile in any way should not be acting as an oxidizing agent, so that electrophilic substitution reaction on the ferrocenyl ring take place, and if it does otherwise, that means it acts as an oxidizing agent, then ferrocene will be oxidized to ferrocenium cation, and then the electrophilic substitution reaction would not be happening. And the last thing that we had discussed in the previous lecture is the approach of the electrophile, and it has been proven by elegant experiments in which it was convincingly showed in a tricyclic CP system that this approach of the electrophile occurs from the exophase in a facile manner as opposed to the endophase, and this also again is a conventional wisdom because of steric resonance. The attack from the facile phase is more favored. Now, in today's lecture we are going to discuss something very intriguing. We have seen that this electrophilic attack occurs, but we are going to dwell on another interesting aspect of ferrocenyl chemistry, particularly lithiation reactions of the ferrocenyl ring. Now, these lithiation reactions of ferrocenyl ring is kind of challenging because these lithiation reactions occurs uncontrolled, and as a result there are mono di lithiation or even trilithiation of ferrocene that occurs. So, the lithiation of ferrocene is hampered by multiple lithiation of the CP ring. Now, lithiation is an important reaction because lithiation gives rise to various other kind of substitution on the CP ring. So, uncontrolled lithiation of the CP ring make the normal conventional lithiation of ferrocene reaction kind of not very useful. So, in this perspective, finding a controlled lithiation of the CP ring was of utmost interest, and that was the need of the day. And the solution arises to this is via Stanyl derivative, which is shown over here. So, the metallation of the ferrocene is hampered by multiple lithiation, and as a result, as a recourse to this, organo-stanyl ferrocenyl compounds are often used. So, or organo-stanyl ferrocene compounds provides the welcome relief to multiple lithiation issue. So, this is kind of a very useful method for putting various kinds of substitutions on the ferrocene ring, which otherwise could be easily achieved by lithiation in other organic compounds. So, I am going to illustrate this in much more details in next few minutes of our discussion. For example, the treatment of ferrocene with T-butyl lithium in THF hexane at 0 degree centigrade and in presence of tributyl tin chloride gives a mixture of compound which is some unreacted ferrocene plus ferrocene with tributyl tin and plus doubly stannated tributyl tin compounds. Now, the reaction this mixture is like the stanyl ferrocene compound is the major product. So, this is about 66% and the di-stanyl compound is very little, which is about 7%, and the unreacted ferrocene is about 33%. Now, the reaction of this monostanyl compound with various reagents, for example, aryl bromide in presence of DPPY PaDCl2, copper oxide DMF 100 degrees centigrade. So, this is nothing but the Stille reaction or CC cross coupling reaction gives this aryl substituted ferrocenyl compound. So, steely coupling similarly, the mono tributyl stanyl ferrocenyl compound reacting with iodine gives the iodine substituted ferrocenyl compound as well as the organostanyl derivative with butyl lithium in THF at minus 78 degrees centigrade eliminates tetrabutylene, giving the much desired monolithiated compound. So, this is just simple transmetallation reaction, and that when treated with triphenyl phosphine chloride, diphenyl phosphine chloride would give the phosphonated ferrocene compound. So, what we see is a nice example of beautiful chemistry laid out over here. As we saw that lithiation or multiple lithiation was the problem with ferrocene if ferrocene is treated with simple butyl lithium. However, that problem is circumvented by treating this with tributyl tin chloride as an electrophile and then preparing mono substituted tributyl tin ferrocenyl compound in major amount, and then subsequent treatment of this mono butyl ferrocenyl compound with aryl bromide in presence of palladium, doing a regular steely coupling resulting in the aryl substitution of the same, treating that with normal iodine as an electrophile will give the iodide compound, as well as treating this tributyl stanyl ferrocenyl compound with butyl lithium exclusively gives the monolithiated product, which when treated with PH2 phosphorus chloride, PH2PCl, this is PH2PCl, gave the diphenyl phosphine derivative of the ferrocenyl compound. So, this organostanyl ferrocene provides a useful route to so many different compounds, and that solves the issue of multiple lithiation, which usually plaguing the normal lithiation chemistry of ferrocene. So, this is where one can see that how chemists primarily circumvent many complicated issues, not only by making a derivative and then successfully making what really it wants it to make. For example, in this case the chemist found a method to really make this monolithiated product successfully, even though they had to go make it via this organostanyl ferrocene derivative, which they made from ferrocene. So, this is the way you can see that one can avert or avoid issues by coming out with a novel approach in making them. So, here we find the example a beautiful demonstration of chemistry and also various protocols, including the one to make the monolithium lithiation of ferrocene in a successful manner. Similarly, the dilithiation in a selective manner of ferrocene has been achieved, and this has been done in presence of by doing the reaction in presence of TMEDA. in hexane at 25 degrees centigrade gives exclusively the desired dilithiated product. Plus 2/3 okay. Now another important feature about ferrocene is that it stabilizes a carbocation which is adjacent to it. I will illustrate that with the example over here now. For example, so this alpha carbocation is sort of stabilized as a result of loss of this acetic acid moiety, and that can pick up water to give. This is sort of the transition state to give the alcohol now. It is important to note that there are like this transition state, which is a cationic alpha carbocation, has been successfully characterized by X-ray crystallography by putting various substituents, where it sort of explains the fact that this cationic charge is highly stabilized by this CP ring, and that also again is an obvious conclusion given the fact that the CP rings are carbanionic in nature. So, if there is a positive charge in the alpha position, so that gets stabilized readily, and this has been done even using X-ray crystallography. So, with this we are going to move on to some important variants of transition metal cyclopentadienyl complexes, particularly the cyclopentadienyl carbonyl complexes. So, we are just moving away from binary cyclopentadienyl transition metal complexes like metallocene Cp2M, which are homoleptic complexes, to heteroleptic cyclopentadienyl metal carbonyl complexes. So far in the last few lectures, we have been discussing about Cp2M type of complexes, which are called metallocenes, or sandwich complexes. These are binary Cp complexes, or even homoleptic complexes. From these, we are going to move to Cp-M CO N type of complexes. These are cyclopentadienyl metal carbonyl complexes, which are no longer metallocene. They are called half sandwich complexes. And also they are no longer binary complexes, because now there are more than 2 different kinds of ligands. So, these are called heteroleptic complexes. So, these are particular special kinds of variations of bis CP iron complexes, in the sense that one of the CP ring has been removed and is placed replaced by carbonyl metal complexes. So, the next part of this lecture, we are going to talk about various synthetic methods that are available for preparation of cyclopentadienyl metal carbonyl complexes. The first and the foremost, the cyclopentadienyl metal carbonyl complexes are directly prepared cyclopentadienyl transition metal carbonyl complexes are prepared by metal carbonyl and the CP ligand. This is illustrated by the reaction of FeCO5 or ruthenium CO12 and cyclopentadiene, giving the cyclopentadiene complex of metal tricarbonyl, which loses a carbon monoxide, followed by this aromatization of the cyclopentadiene ring, resulting in a metal hydride complex and which eventually eliminates hydrogen to give the dimeric compound. And over here the metal is equals iron and ruthenium. Similarly, along the same line, the reaction proceeds for the Cp star derivative. For example, the reaction of CO10, Hc5, Me5, hydrogen. This occurs at very high temperature. Give Cp star, rhenium, loses to give this beautiful compound containing rhenium triple bond with bridging carbonyl. Okay. So, this is a very elegant compound which is prepared from the reaction of dilanium dodecacarbonyl with Cp star pentamethyl cyclopentadiene. By heating them at 200 degrees centigrade at very high temperature, it caused Cp star rhenium tricarbonyl, which in presence of light loses these 3 carbonyl moiety to give this rhenium-rhenium triple bond with 3 bridging carbonyl atoms. So, with this I would like to draw conclusion to today's lecture. Today's lecture had been on looking at the reactivity of transition metal cyclopentadienyl complexes, and with the main emphasis in today's reaction is was on trying to look at the challenges that lied with a simple metal lithiation chemistry of ferrocenyl compounds, and the ways and means to come around it. The primary challenge that we had discussed about the lithiation chemistry of ferrocenyl compounds is the fact that it would undergo multiple lithiation, which would hamper this process of lithiation without giving any selectivity to the lithiated product, and that was judiciously overcome by preparing a mono organometallic ferrocenyl compound, which was predominantly formed, and subsequently then converting this organometallic ferrocenyl compound to various other derivatives through simple Stille coupling or various kind of electrophiles, or even by treating with butyl lithium, successfully converting it to a monolithiated compound, which again can be reacted with various electrophiles to get that. We had also seen in our discussion that under certain conditions, particularly in presence of TMEDA, one could successfully isolate the dilithiated product where the lithiation had occurred on each of the 2 rings. We have also come upon the discussion on the stabilization of cationic charge at the alpha position of the cyclopentadienyl ring, and that we had seen have been used in making alcohol substituted ferrocenyl compounds. The reason for successful stabilization of the alpha carbocation adjacent to the ferrocenyl ring is kind of due to the obvious resonance that arise out of this highly conjugated electron rich carbon ionic nature of the cyclopentadienyl ring. Now, having discussed the reactivity of cyclopentadienyl transition metal complexes, we moved on to one of its variant, which are these half sandwich heteroleptic transition metal carbonyl complexes, and looked into various methods for preparing this compound. The methods that we have today discussed upon is the direct reaction of metal carbonyl with the cyclopentadiene olefin compounds, resulting in this half sandwich cyclopentadienyl carbonyl compounds. So, this is pretty useful method and kind of generic method and results in the expected compound. We had seen the formation of beautiful metal-metal triple bond, particularly in case of rhenium, appropriately stabilized by Cp star ligand. So, with this I am going to conclude today's lecture. We are going to discuss in more details about various preparative as well as reactivity patterns that remains to be discussed for transition metal cyclopentadienyl carbonyl complexes, and then move on to some other variants of it, particularly the nitrocell compounds in the next lecture or the subsequent lectures. So, with this I once again thank you for patiently listening to this lecture, and I look forward to being with you in the next lecture. Till then, goodbye and thank you.